So in this lesson, we're going to put everything together. The idea of specific heat capacity, things warming up or cooling down, and latent heat to take into consideration when materials change state. So let's have a look at this situation here, which is a little bit complicated. You've got water at room temperature, about 23 degrees, and you put it in a kettle, which heats up and then boils for 5 minutes until 30 grams of water boils away. So what we've got there is a complex situation because heat is coming in from the stove, right? And the water, remember, was at 23 degrees. So that water has to go up to boiling. So you have to use this idea of specific heat capacity and Q being used to increase the temperature up to 100 degrees of that water. Not only is the water getting hot though, the kettle is also getting hot. So some of that Q energy is also increasing the temperature of the container. And then once the temperature of the water reaches 100 degrees, then some of that Q is being used to change the state of that liquid into gas. So we have quite a complex equation. And this is what our equation would look like. Q, the heat energy in joules, would go to increase the internal energy of the kettle. The kettle itself will get hot, plus the increase in internal energy of the water. So you will heat up the water from 23 degrees up to 100, plus the energy of the vaporized water. So the energy of those 30 grams as it changes into a gas. So that's how we build our equation. And then we substitute in our actual variables. So you can see here, the heat energy coming in joules would be equal to mc delta T for the kettle. So you'd have to use the mass of the kettle, the specific heat capacity of the kettle, and the change in temperature of the kettle from room temperature to whatever temperature it gets up to, plus the mass, the specific heat capacity, and the change in temperature of the water up to 100 degrees. And then we have the energy of the vaporized water. So that would be the mass of the water that's changed into a gas times the latent heat of vaporization. Now this is the most complex situation you could pretty much come up with. Here's a question. 120 grams of water at 23.5 degrees was poured into a plastic tray for making ice cubes. So there we go. It's always helpful to actually look at something. So we've got water being poured into a plastic tray to make ice cubes. The tray was already at 0 degrees. Okay, so we don't have to cool the tray down, which is helpful. Calculate the thermal energy that has to be removed from the water to turn it all into ice. Now, if we use the same idea as in the previous slide, that Q that has to be removed is basically the energy of the water at 23.5 degrees. That has to be brought down to 0, right? First, if the tray was at room temperature as well, you would also have to remove the energy of the tray. But luckily in this question we don't have to. And then the last thing is, once the water has reached 0 degrees, you also now need that energy to turn it into ice, right? So you need to remove the energy needed to freeze the ice. And so our question comes down to Q equals mc for water, delta T, which would be from 23.5 all the way down to 0, plus ml, which is the energy removed to freeze the ice. Have a go at that question. You should get 5.4 times 10 to the 4 joules. Now the second type of question, which is a little bit more complex, is when you start to mix up specific heat capacity with mechanics. Because energy changes, the energy changes that you came across in 2.3, from potential to kinetic, from kinetic to sound to heat, etc., usually they involve increases in temperature. When you lose energy as heat, something gets warmer, right? And you can tell that if you rub your hands together. If you rub your hands together now, you find that the kinetic energy of your hands becomes heat energy and your hands get warmer, right? So we can apply specific heat capacity to this in order to work out what the temperature of the object is. So this car here, for example, has stopped rather suddenly. All of that kinetic energy has been converted into heat energy, and you might find bits of this car have gotten very hot. So let's have a look at how we will deal with that. Half mv squared, if we have a situation where all the energy is lost as heat, would be equal to mc delta T. Now, as you know, some situations are inefficient, not very likely. This is a bit of an unusual situation where all the energy is becoming heat. But sometimes you'll have an inefficiency. So for example, if you have a situation where it's only 30% efficient and the rest is lost as heat, then 70%, it would be 70% of whatever energy is produced or being used as an input would be equal to mc delta T. I hope that made sense. Have a go at this question then. A car of total mass 1,200 kilograms traveling at 17.3 meters per second has 4 disc brakes. Calculate the kinetic energy of the car. Estimate the maximum temperature rise of the brakes when they are used to decelerate the car to rest. So in this case, all that kinetic energy has turned into heat, and use that to work out the temperature rise. The increase in temperature should turn out to be 67 degrees, which is rather a lot.